Thank you very much for the opportunity. I'm just talking about one of the projects we're doing as part of the data science and informatics core for cancer research at UT Health. Right. Okay, so for this project, what we try to do is we try to identify disease, predict disease comorbidity. What diseases they might be closely related, or maybe, they will, if happen together, patient will have a very severe consequence. Example is like COVID-19. For healthy person under age of 55, the risk is very low. But if combined with other conditions, health conditions, then it might be have a severe consequence. So that's what we try to do here. Okay, so this kind of disease relationship has been started by several groups, and there are some publications about that to try to understand how diseases are related. So, for example, people have developed methods based on clinical data and also based on the molecular interaction, disease gene association, causative proteins, like, what the protein cause, if mutated, cause what disease, those kind of information, as well as, an integrative approach, integrate multiple data sources, try to predict how diseases are related. But the challenge is, like, for example, you have incomplete information, people focus on very specific disease or a very small set of disease, and also, not generalized enough, just focus on a special population or cohort. And also, there's a very big challenge about how to predict, like, indirect association. There's always, situations where you have to have some manual intervention for computation approach. So here, what we try to develop is to integrate the literature as well, as other information. Try to develop a generalized model that can integrate this information to predict the disease relationship. So here's the overall structure with us 3 different phases. So in general, we try to use a symbolic entity encoding that includes a fingerprint part, which basically extract the information from the literature, use controlled vocabulary, and we perform the enrichment analysis to build encoding with the enrichment p-value. And we combine that with a general embedding model that is flexible, with a good performance, but also with the limitation of uninterpretable and unportable. So by combining these, our algorithms can achieve a better performance. So as part of this algorithm, the first step is we try to do a convolutional enrichment representation to extract useful information from the literature. We do a random sampling the abstracts with the replacement, try to perform the enrichment analysis on the terms that is biologically relevant. And then we, with this enrichment analysis, then we'll adjust the p-value to build this enrichment representation for the disease. Once we have that, then we use an autoencoder to extract the feature from this representation. And this also allows us to try to identify the latent representation and the feature as well. And on top of that, we will do this autoencoder will also do the dimension reduction. Now, with the with these embedding generated from the autoencoder, Then we'll combine that with the word-to-vec embedding, and then we take these two feature sets together and then use the autoencoder, we train, and we magnify the features. Here are the data we used. We used the 41 million PubMed and abstracts, and then we take about 38,671 Homo sapien genes. And then we also take the human disease network that includes 517 diseases in 22 classes. And there's 278 diseases in MASH term. And then we take the connections of this disease that there are 1,188 connections with 521 connections among these 278 diseases. And we also have these negative training data sets that without any connections, and for as the negative training for the project. So here's a comparison of the performance with the different methods. These are the methods by other people. Fingerprints is the original methods we developed. The new method performed much better than the other methods with a significant improvement. We apply this approach to predict what are other diseases that are related to COPD, which is a very bad lung disease. We took the lung disease branch on the MASH term, and then we try to identify what are the diseases related to the COPD, and then we ask the experts to evaluate our predictions. And out of the 80 diseases, we predict 36 positives and 24 negatives that are consistent with the five experts evaluation. These are the clinicians with years of experience in the COPD and other lung diseases. And for the rest that we didn't predict, they also cannot have a consistent consensus among these five experts. We also apply that to coronavirus-related comorbidity and other diseases. I will show results later. We also have applied these methods for evaluation with disease gene association, basically try to identify what are the important genes for each diseases. And for most of them, we reached the AUC of over 85%. So we are also working with domain experts on several other diseases like Alzheimer's disease, lupus, and glioblastoma. So here's an example of the coronaviruses. So we try to apply these to identify what are the other diseases that might be, combined with coronavirus that can have severe consequences, or have these patients who contracted coronavirus, even if they recovered, they might have other diseases as a consequence of the coronavirus infection. Here are the overlap between our prediction with the CDC and with the one set published by Lancet. But in addition of that, we also identified some other diseases that we think are related to coronavirus infection. One interesting example is this pigmentation thrombophilia. So we predict this disease, and that we think may be related to coronavirus infection, or as a consequence of the coronavirus infection, there are some abnormality. And then there are several cases report that patients who are infected by the virus actually have very dark skins and things like that. So it's kind of, we're kind of looking into the possible connection there with regard to this finding. With that, I'll just stop here. And this work is mainly done by Guocai, Chen in my group and several other people together with domain experts at the UT Health. Yeah, so.
In your previous slide, you mentioned hypertension, but picked up heart disease.
Right, okay, so yes. It's very interesting about these three terms. For whatever reason, in the mesh that we take from that branch, these three ones are left out. So we were very surprised that, why these three obvious ones were not predicted. And then we trace back to find what's the reason. And it turned out it's like a technical issue, yeah.
I think one thing that kind of stood out to me, the previous, okay, so we have these imperfect representations, the mesh, all, it's,
right.
The disease depression is actually probably 5 diseases. Could you use some of your work to kind of redraw what it should look like?
Right, yes. That actually, I think goes back to some of these lung disease that we have these predictions, and then we have these 5 clinicians to say, how these, there are diseases, they don't have any consensus, which means that, probably the current definition or, the clinical diagnosis have some kind of a murky area, and that's where these might be helpful. Yeah. Right. Yes, that's actually a very good question, right? Yeah. So that is exactly why we use this random sampling with the replacement, because in our original work we just did enrichment analysis without considering about there is like overrepresentation of well-studied diseases or genes versus rarely studied disease and genes. And so by the random sampling, then we kind of even that out. It actually helped quite a bit by that.